Good everyone, welcome to Insight Tutorials. So today we're going to be treating 35 high-yield questions in physics if you're preparing as a university student for your exams. This very question is going to guide you through. All right, so take a pen and paper and do well to follow suit in solving even before I reveal every answer. So let us get straight away into solving the questions. Now, these questions are actually mapped out here. The first question says that which scientists researched and theorized about the Earth's magnetic properties? A says Isaac Newton, B says Albert Einstein, C says William Gilbert, and D says Michael Faraday. Looking at all of these scientists, it's very pertinent for you to know that Isaac Newton here is the man that is attributed to anything that has to do with mechanics and gravitation. Michael Faraday is synonymous to electromagnetic induction. When we talk about Albert Einstein, we're talking about special relativity. So it happened that the scientist that became an early pioneer of the study of magnetism, who theorized that the Earth is seen as a giant magnet, is William Gilbert. So this is the correct answer. It was William Gilbert that was scientists that researched and theorized about the Earth's magnetic property. That is important for you to know. Question 2 says, which reaction involves the target nucleus picking up a nucleon from the projectile? Now, this has to do with nuclear reaction. In nuclear reaction, there's something you need to know. Every time a particular particle is projected and it hits the target, something happens. Now, it's either the proton is sent back and the neutron is emitted, or vice versa. Now, for nuclear reaction of this manner, what you need to understand is that when nuclear reaction occurs, we have it written in a part where we have the target plus we have referred to as the projectile and then the emitted particle. Now, what you need to understand is that this D here means a deuterium, and this P means a proton. This P is also a proton, and this D is a deuterium, and this N is a neutron, and this is alpha particle. This is alpha particle, and this is a neutron. And the question says that which reaction involves the target nucleus picking up a nucleon? Now, when you hear the word nucleon, you know that it's actually a makeup of the proton and the neutron. All right. Now, for there to be picking up, there can either be a picking up. When a nuclear reaction occurs, there can either be a picking up or a giving off. Now, under what condition is there a picking up? If this is actually our reaction, there's going to be a product. If this is a reaction, there's going to be a product. Now, that product is going to produce, now we're going to write the product plus proton. Now, what does that imply? A deuterium, when we say nucleon, remember I said nucleon comprised of two major things, the proton and the neutron. Now, a deuterium also consists of that. A deuterium consists of one proton plus one neutron. Now, for it to be a picking up of a nucleon from a projectile, we'll have it that what will come in contact with the target, this projectile is the incoming particle, and this emitted particle is the outgoing. So you take it to be more like when you impute something into a reaction, what comes out and what remains. That's what we're trying to say. So in essence, if it's a nucleon that is actually sent out, and that's a deuterium, right? When it is sent out, what happens is that it sends back the proton, but then takes up or picks up the neutron. All right. And if it picks up the neutron, what you have in the product will be the proton. All right. Now, what you need to just understand in essence is if it is picking up of reaction, you simply, it's going to be the deuterium and the proton. But if it is giving off, it's going to be the proton and the deuterium. Now, the key thing you need to understand is that if what is being sent in is bigger For example, the deuterium has two, which is one proton and one neutron. That's two particles, right? If it is what is sent first, that is a projectile. Remember, the projectile in this case is deuterium, and since the deuterium that is sent out there's going to be an absorbing of the neutron and a sending back of the proton. So this kind of reaction is called picking up. What is picked up? The neutron. Then in terms of the giving off here means it is actually proton that is projected. And if it is proton that is projected, there's going to be what? A giving off. Giving off of what? Of the neutron, so that the deuterium can still be formed. All right? And that is what you need to understand. So anything has to do with this kind of question, understand picking up and giving off. Picking up is when it is the larger particle that is actually projected, all right, which is deuterium. It takes the neutron and then sends back the proton in the product. But then if it is giving off, it's actually what? It sends back, it gives off the neutron, all right, and then so that it can actually form what? The deuterium. So the correct answer to this question is deuterium to what? Proton. All right. Question 3 says an electromagnetic wave takes how long to travel 1.5 times 10 to the power of 9 meter in a vacuum? Take note of the word in a vacuum. If it was not in a vacuum, we'll have it that our velocity is equal to distance all over our time, right? Now, for us to calculate time, we'll say that velocity times time is equal to distance, so that time is equal to distance all over velocity. Now, since it is in electromagnetic wave, since we are dealing with electromagnetic wave, right? Since electromagnetic wave, this velocity will actually be giving us the speed of light for us to be able to get how long it will take. So in essence, we're going to say that time is equal to distance all over the speed of light, where this is giving us 1.5 times 10 to the power of 9 all over 3 times 10 raised to the power of 8. So if we punch this in my calculator, 1.5 times 10 raised to the power of 9 divided by 3 times 10 raised to the power of 8. So it happens that the time is 5 seconds. So it's going to take 5 seconds to travel 1.5 times 10 to the power of 9 meters in a vacuum. Our next question says, let me make some space for solving question. So in this particular question, our answer is 5 seconds. Question 4 says that when a 5 microcoulomb test charge is placed at a point, it experiences a force of 2 times 10 to the power of minus 2 Newton. Calculate the electric field at that point. Now, for us to calculate the electric field of a test charge, it is simply giving us electric field is equal to the force all over the given charge. All right? Now, for us to be able to just do that, we're going to say that the electric field is equal to, our force is 2 times 10 raised to the power of minus 2. All right? Minus 2 all over. Now, our charge was given to us in microcoulomb, so we're going to convert. So instead of, we'll just say 5. Now, to convert coulomb to microcoulomb, we'll simply multiply by 10 raised to the power of negative 6. All right? So we're going to actually do that on our calculator. And I'm going to say 2 times 10 raised to negative 2 divided by 5 times 10 raised to the power of negative 6. All right, so when we did 2 times 10 raised to the power of minus 2 and we divided by 5 times 10 raised to the power of minus 6, we got 4 times 10 raised to the power of 3 Newton per coulomb. So option B is the correct answer. Question 5 says, what is the magnitude of an electric field at a point 2 meters away from a 4 microcoulomb charge? I say we should take electrostatic constant K as 9 times 10 to the power of 9 Newton per meter square per coulomb square. Now, take note of the difference between this question and that question. This one just talked about the electric field in itself, and this one I talked about the magnitude of the electric field. So take cognizance of the formula. Electric field, this is it. But magnitude of electric field. So for question 5, the magnitude of electric field E is giving us the constant K all over the charge times the charge all over R square. That is very, very important for you to know. All right. So then what we're going to do in essence is that our constant was given to us as 9 times 10 raised to the power of 9 times our charge. The given charge was 4 microcoulomb. We're going to convert 4 microcoulomb again. We're just going to impute times 10 to the power of minus 6. It's going to be 4 times 10 to the power of minus 6. All right. All over our distance was given to us as 2 meters. So it's 2 meters whole squared. So this is now 9 times 4 is simply 36 times 10 raised to the power of, according to the law of indices, remember that this is positive and this is negative. So we're going to add the power. All over this is what? 4. So it happened that this is 36 times 10 raised to the power of plus times minus becomes minus. 9 minus 6, that's going to be 3. All over this is 4. So this is equals to, when we do 36 times 10 raised to the power of 3 divided by 36 times 10 raised to the power of 4 divided to the power of 3 divided by 4, our answer is 9 times 10 raised to the power of 3 Newton per coulomb. So it happens that option B is the correct answer. Go to the next. Other question. This says, what is the magnetic flux density of an iron core with a cross-sectional area of 0.2 centimeters square and a magnetic flux of 0.1 microweber? All right. Very importantly for you to know, this is magnetic flux is equals to magnetic field density times the area. Now, if there was a given angle, we're going to put the angle in attachments to this particular formula, but we don't have any angle given in this regard. So this is a formula that will aid us in doing that. Now, before we solve it, so we're asked to find the magnetic flux density. So magnetic flux density is going to be the magnetic flux all over what? The area. Now, for us to be able to do that, we have conversions to do. Our magnetic flux was given to us as 0.1 microweber. So we have to convert 0.1 microweber to what? Weber. And how do we do that? We simply do 0.1 times 10 to the power of negative 6. And by so doing, we've converted to Weber. Sorry for my space. And then we have to convert this 0.2 centimeters square. All right. Now, 1 centimeter is equals to 10 raised to the power of minus 2 in its meter. It's more like you doing 1 divided by 100, right? So it's going to give you 0.01 meter. So if you write it in this particular form, this is how it will be. Then remember that we were not giving this in centimeter, we're giving it in centimeter square. So we're going to say that centimeter in its squared, 1 centimeter in its squared is more like you say 1 times 10 to the power of negative 4 in its meter. Because if you do 10 times negative 2 times 10 times negative 2, you have 10 times negative 4. So in essence, so if we are to convert 0.2 centimeters squared to meter, we're going to say it is 0.2 times 10 to the power of negative 4. That would be the meter conversion of that. Now, let me make space for this so that we'll be able to solve and complete this question. All right. So it happens that our magnetic flux density is equals to our magnetic flux all over our area. And from what we have, our magnetic flux is 0.1 times 10 to the power of negative 6. All over this is 0.2 times 10 to the power of negative 4. And it happens that if we multiply that in my calculator, if we multiply, we're going to do 0.1 times 10 raised to the power of 6 divided by 0.2 times 10 raised to the power of minus 4. Our answer will be 5 times 10 raised to the power of minus 3 Tesla. So it happens that option B is a correct answer. Next question says that what is the force that binds proton and neutron in a nucleus? All right. Now, what you need to understand is that gravitational force is simply a force that acts against an object that tries to actually go out of the Earth's surface. It happens that the particular force that exists when it has to do with nuclear particles is actually what we call the stronger nuclear force. Now, proton in itself is actually positively charged and it exerts certain kind of repulsive force between it. But it stays very, very much together with the nucleus, with the neutron in the nucleus of an atom because of this force. As referred to as what the stronger nuclear force. So the force that holds nuclear particles together in a nucleus is referred to as what? It's a stronger nuclear force. Not the weaker nuclear force. The stronger one actually is what keeps them together, because the weaker it becomes, the more unlikely it is to hold up the proton and neutron together. Now, question 8 says that times get slower near massive objects due to stronger gravitational field. True or false? What do you think is the answer? It's true that as the closer a time or a clock ticks in a stronger gravitational force or is a stronger gravitational field, the slower time gets. Like that's to say that when time actually, the way time is calculated around an object that is massive in terms of its mass, its size, and then when it gets closer to an environment that has stronger gravitational field, time tends to slow under a stronger gravitational field. But the weaker the gravitational field is, the more it allows time, the more an object moves faster around what? An object that's actually massive in terms of its size. So what you need to understand is that the concept is time gets slower, yes, as it moves near to a massive object due to what referred to as what? The stronger gravitational field. All right. So it happens that this particular answer is option A. This statement stays true. All right. Question 9 says the process of earthing is necessary in a gold leaf electroscope for the purpose of A says keeping the casing at a lower potential than cap. B says allowing excess electron on the case, and C says A and B are correct. This is none of the above. What you need to understand is that earthing provides a conducting connection between Earth, right? And earthing actually allows for it serves as a reservoir, particularly for charge, right? And it allows for the flow of those charge in and out of the Earth. All right. So for the purpose of a gold leaf electroscope, it actually serves two important purposes that you need to know. And those two important purposes are stated in option A and B, which is keeping the casing at a lower potential than cap, and secondly, allowing excess electron on the case. So it happens that for this particular question, option C is correct. That houses A and B, because those two actually serves for the purpose of what? A gold leaf electroscope in respect to earthing. All right, so option C is correct. Question 10 now says that the theories of relativity are applied in the following field, except it says GPS system, B says UPS system, and C says particle physics, and D says astrophysics / cosmology. Right? Now, relativity applies to three major of the items stated here, but one of them is not in respect, or one of them does not apply to relativity. We'll talk about astrophysics and cosmology. We're talking about black holes, stars. So it actually relates to what? The theory of relativity. We'll talk about particle physics. You know, particle, when they travel, they actually move closer to the speed of light. So we'll actually need the theory of relativity to explain that concept as well. GPS systems are also very important in terms of the satellites. You know, for you to be able to understudy it, you need the application of relativity. UPS system is out of the picture, uninterruptible power supply system. It does not necessarily require what? The application of what? Relativity. So that's out of it. So the option B is correct. Go to the next. All right. Question 11 says that isotopes have equal number of neutrons, have A says equal number of neutrons, B says equal number of protons, C says equal number of neutrons but unequal number of protons, D says none of the above. Now, what you need to understand about isotopes are simply elements of the same atom, the same atomic number but different mass number. So when we talk about atomic number, we're talking about the number of protons in that particular nucleus of an atom. For example, if we have carbon that has 14, we have another carbon with 12 in its mass number, different mass number but the same atomic number. That is what isotopes are all about. Now remember, there is sameness in their atomic number, and if there is sameness in the atomic number is simply the number of protons in the nucleus of an atom. So what agrees with isotopes here is that they have equal number of protons. Question 12 says that find the value of the Lorentz factor if the speed v equals 0.6 c, that's the speed of light, where c is the speed of light. So for us to solve this question is very simple. We're simply going to say that our Lorentz factor is going to be 1 all over the square root of 1 minus the speed of the object squared all over the speed of light squared, which will be giving us 1 all over. Now we are giving our velocity at 0.6 the speed of light. So we're simply going to say it's the square root of 1 minus, this is 0.6 the speed of light in its squared all over speed of light squared. So Lorentz factor is going to be 1 all over 1 minus, if we square the 0.6 times 0.6, is going to give us 0.36. C times C is C squared all over, there's another C squared. So C squared can cancel C squared. So Lorentz factor is going to be 1 all over the square root of 1 minus 0.36, which is equal to 1 all over the square root of 1 minus 0.36 is 0.64. And if we do 1 all over the square root of 0.64, let us find the square root of 0.64. Square root of 0.64 is 0.8. So 1 divided by 0.8 is 1.25. So it happens that our Lorentz factor is 1.25. So it happens that option B is correct. Question 13 says, choose the correct statement for nuclear charge. Now, one of the key things you need to know about key properties or element of the nuclear charge, look at all the options, is that number one, the nuclear charge is very strong. Number two, it has short range, right? Then number three, it's actually charge dependent. These are the key three properties of a nuclear charge. Number one, I said there it's very strong. Number two, it is short ranged. Number three, it is charge dependent. And it happens that the option that actually agrees with those properties of nuclear charge is option A. Take cognizance of that very importantly. Question 14 says that charging a body can be achieved by A says contact, B says friction, C says induction, and D says all of the above. Now, it happens that for you to charge a body, you need the application of each of these. Contact implies that you bring a charged body in contact with another body that is not charged. There's going to be a transfer of charges. Friction has to do with rubbing off of a charged materials with another one. There's actually going to be transfer of charge as well. Induction, where charges are transferred without making contact with each other. So these three processes are very necessary for charging a body. So the option that is correct is all of the above. Question 15 says that calculate the magnetic field strength of a current of 5 ampere through a wire of length 0.2 meter and that experiences a force of 0.5 Newton. Let me make space here and write out this particular question. I left it at this junction without an option. And I want you to think, what do you think would be the answer if you had to solve this without an option? So let us solve this question. Now, the force on the current carrying wire is simply given as the given force is equal to the magnetic field density or intensity or the magnetic field strength times the current times the length. Assuming that the force is maximum, right? Or assuming that it is perpendicular, this is actually the formula that agrees with it. And we are told to calculate the magnetic field strength, meaning we are looking for this, right? So it happens that magnetic field strength is going to be force all over the current times the length. And from what you are given, we have it that force all over the current times length is equal to, now our force is given as 0.5 Newton. And then our current, we're given a current of 5 ampere times the length was given to us as 0.2. So we can actually work that through our calculator. So if we have, so this is, let's say 0.5, all over 5 times 2 times 0.2, we got 1. So if we divide that, we're going to have 0.5 Tesla. All right, question C says, calculate the inductive reactance of an inductor with an inductance of 50 millihenry with a frequency of 100 hertz. These are the options we are given. Now, for you to be able to find the inductive reactance of an inductor, the inductive reactance is a symbol is equal to 2 pi frequency times what's the inductance. Now, from our given question, we're given a frequency of 100 hertz. And we're given an inductance of 50 millihenry. So it happens that we're going to convert this 50 millihenry to Henry. And to convert millihenry to Henry, simply divide by what? 100. We're going to say our inductance is 50 divided by 100. It's going to give us 0.5 Henry. We're going to just substitute into this formula and get our answer. So 2 times pi is always given as 3.142 is constant, times 100 divided by frequency times 0.5. Let us multiply that. 2 times 3.142 times 100 times 0.5. So it happens that our answer is 31.42 ohms. So option C is correct. Now, having gotten that, we'll make space again to solve question 2. Question 17 says, calculate the force of a repulsion between 2 electrons of magnitude 1.6 times 10 to the power minus 19 coulomb each. If the distance between them is 1 times 10 to the power minus 10 meter, take the K constant to be 9 times 10 to the power of 9 Newton meter square per coulomb square. So we all know that the formula for that this Coulomb's law, and force is equals to the constant K, the first charge and the second charge all over the distance square. Now what you need to know is that they said electron of magnitude 1.6. Now they say each. That means the 2 charges, the 2 electrons we have in this question are both 1.6 times 10 to the power of minus 9. So we can actually rewrite our formula as force is equals to this constant squared all over r squared, since they are both of the same electron. So our given force will be equals to our constant of 9 times 10 to the power of 9 times is 1.6 times 10 to the power of negative 19 all in its squared all over our radius is, the distance is given as 1 times 10 raised to the power of negative 10 in its squared. To work on that, to have it that our force is 9 times 10 raised to the power of 9 times 1.6 times 1.6 times 10 raised to the power of minus 19. It happens that it's equals to 2.56 times 10 raised to the power of minus 38 all over 1 times 10 raised to the power of minus 10 in its squared is simply 1 times 10 to the power of minus 20. So if we multiply that, if we multiply my calculator on, if we multiply 9 times 10 raised to the power of 9 times 2.5 times 10 raised to the power of minus 38, divided by 1 times 10 raised to the power of minus 20. It happens that our answer based on this question is equals to 2.3 times 10 raised to the power of minus 8. Minus 8 Newton. So it happens that the correct answer to this question is option A. Right? Question 18. Let's go to quick. We are done with this. Let me make space so that we'll calculate. Question 18 says that calculate the energy stored in an inductor with an inductance of 10 millihenry and a current of 2 ampere. So anytime you are asked energy stored in an inductor, all right, energy stored in an inductor U is given as half of the inductance times the current in its squared. All right, so this is equal to half times our inductance was given to us as 10 millihenry. Remember, we have to convert to what? Henry. How do you do that? Simply do what? 10 divided by 100. If you divide it by 100, you have 0.1 times our current is 2. So we're going to square it. So it's 2 raised to the power 2. It happens that this is 1 over 2 times 0.1 times, this is 4. 2 here, 1, 2 here, this is 2. So let us do 1 times 0.1 times 2. Our answer is 0.2 joule. So it happens that option C is correct for this particular question. Question 19. Question 19. Let me make space here. This will help us in calculating question 19. All right, it says calculate the energy release when a positron bombards an electron. And the paper gives electron mass constant of 9.1 times 10 to the power of minus 31 kilogram, and the speed of light is given as 3 times 10 raised to the power of 8 meters per second. So it happens that for an electron, the energy will be given as mass times the speed of light squared. Also for a positron, it will also be given as the energy is mass times what? The speed of light squared. So if you are to get the energy total, I'm going to simply add what the electron energy is and to the what the positron. So it's more like you're having mass and the speed of light squared plus mass and the speed of light squared. So you're going to have it that the energy total is going to be 2 the mass and the speed of light squared. All right, so that's what we're going to use in solving this question. So in dealing with that, we're going to say that this is 2 times 9.11 times 10 to the power of minus 31 times 3 times 10 to the power of 8, all in its squared. So we're going to multiply this all at once. 2 times 10 to the power of 9, 2 times 9.11 times 10 to the power of minus 31 times 3.8 to the power of 8, and 3 times 10 to the power of 8 times 3 times 10 to the power of 8. Suppose that our correct answer is 1.64 times 10 raised to the power of minus 16 joule. So option C is correct. All right, question 20 says that calculate the energy of photons if the wavelength of light is 1.5 times 10 to the power of minus 23 meter. Now, remember that energy of a photon is given as the Planck constant times the frequency. Now, because it's actually wavelength of light, all right, and we're given our Planck constant and the speed of light, remember that the speed of light is given as what? Our frequency times our wavelength. Where if we are to substitute frequency in this equation, we're going to say frequency is equals to what? The speed of light all over wavelength. So we're going to substitute this particular formula in this, since frequency is the same thing as the speed of light all over the wavelength. So our energy is going to be Planck constant all over the speed of light times what? The wavelength. So now we're going to substitute this. Energy of a photon is our Planck's constant is 6.6 times 10 raised to the power of here minus 34 times our speed of light, which is 3 times 10 raised to the power of 8, all over the wavelength, which was given as 1 3.5 times 10 raised to the power of minus 26. So I'm going to punch my calculator so that we'll get the answer to this question. So 6.6 times 10 raised to the power of negative 34 times 3 times 10 raised to the power of 8. All right, divided by 1.5 times 10 raised to the power of minus 26. The answer we got here is that the energy of a photon is 13.2 joules. So it happens that the correct answer is option B. All right, so for now, we've come to the end of these questions. I hope these 20 questions will be able to solve. You practice it effectively and do also a robust study preparation for your exams. Do well to always follow us on Tutorial, and don't forget to subscribe, share, and follow us. Thank you very much. Have a nice day.